Welcome, students, to our unit on chemical reactions. In physical science, we explore how substances transform to shape the world around us. Over the course of this lesson, we will learn how to write chemical equations, perform calculations, and analyze energy changes. Understanding these concepts is essential because chemical reactions are happening everywhere, from the cells in your body to the stars in space. Let us begin by looking at our main topics. Here are this lesson's learning targets. Represent chemical reactions using both word equations and chemical formulas. Interpret and balance chemical equations to show the conservation of mass. Identify and classify different types of chemical reactions, and explain how the rate of a chemical reaction is affected by various factors. This is this video's essential question. How do chemical reactions occur, and what factors influence their representation, classification, and rate? Chemical reactions are not just for laboratory experiments. They are happening around us every single second. For instance, metal pipes rust when they are exposed to moisture, and car engines burn fuel to produce energy. Even inside your own body, your stomach chemically breaks down the food you eat. Photosynthesis is another vital reaction, which is defined as the process where plants convert sunlight into chemical energy. So the key point here is that chemistry is a constant part of our daily life. Next, let us define what a chemical reaction actually is. A chemical reaction is defined as a process where substances transform into entirely new substances. The original materials you start with are called reactants, and the new substances that form are called products. As the diagram of water formation shows, the atoms in the reactants are simply rearranged to make the products. Bonds are broken and new bonds are formed, but no atoms are created or destroyed. This is like dismantling a Lego castle to build a Lego ship. You are using the exact same blocks to make something completely different. Let us discuss how we can actually observe these reactions in real life. When a reaction occurs, three major changes take place. Reactants disappear, new products with different properties appear, and energy is released or absorbed. We can detect these changes through 5 visual clues, such as color changes, gas bubbles, or the formation of a precipitate. A precipitate is defined as a solid substance that forms from a liquid solution. It is like baking a cake, where the raw ingredients transform completely. Next, we will learn how to write these reactions. To communicate chemical changes, scientists write equations in 2 different ways. The first method is a word equation, which has a qualitative meaning because it only identifies reactants and products by name. For example, when hydrogen gas and chlorine gas combine, we write hydrogen plus chlorine yields hydrogen chloride. This is like writing a shopping list. It tells you what you have, but not how much. So the key point here is that word equations are simple, descriptive representations of a reaction. Let us practice writing a word equation with a quick pop quiz. Let us work through our first pop quiz together. We heated a strip of magnesium metal in oxygen gas, producing a white powder called magnesium oxide. To represent this using a word equation, we write the names of the reactants on the left and the product on the right. Magnesium and oxygen are the reactants, and magnesium oxide is the product. The arrow shows the direction of the reaction and means reacts to form. Word equations help us describe reactions clearly before using symbols or formulas. In this reaction, zinc metal is placed in hydrochloric acid, and bubbles form on the metal surface. The bubbles indicate that a gas is being produced. This gas is identified as hydrogen. At the same time, zinc chloride forms in solution. To write the word equation, we list the reactants zinc and hydrochloric acid, followed by the products zinc chloride and hydrogen. This word equation shows both the new substance formed and the gas released. Chemical reactions can also be written using chemical equations. Unlike word equations, chemical equations use symbols and formulas to show exactly what happens. The plus sign means and, while the arrow means reacts to form. Symbols like S, L, G, and AQ show the physical state of each substance. These equations clearly identify the reactants and products and make reactions easier to analyze and compare. Dalton's atomic theory helps us understand chemical reactions at the particle level. It states that matter is made of atoms, and atoms of one element are different from atoms of other elements. During chemical reactions, atoms are not created, destroyed, or changed into other elements. Instead, atoms are rearranged to form new compounds. This idea leads to the law of conservation of mass, which says that the total mass of reactants equals the total mass of products in a closed system. In other words, the same atoms are present before and after the reaction, just arranged differently. Stoichiometry is the study of quantities in chemical reactions, and it is built on the law of conservation of mass. This law states that mass is neither created nor destroyed in a chemical reaction. Antoine Lavoisier demonstrated that the total mass of the reactants is always equal to the total mass of the products. In other words, the same atoms are present before and after the reaction, just rearranged into new substances. So the key point here is that matter is always conserved. These are the core rules for balancing chemical equations. Rule 1 is conservation of atoms. Every element must have the same number of atoms on the reactant and product sides, since chemical reactions only rearrange atoms. Rule 2 explains what you are allowed to change. You may change coefficients, which adjust how many particles react, but you may not change subscripts because they change the identity of the substance. The final rule is about the answer format. Balanced equations must use whole number coefficients, and they should be the smallest whole numbers that keep the equation balanced. Fractions are not allowed in final balanced equations, so the key point here is that we must always use whole numbers to represent complete molecules. This shows the first step in balancing a chemical equation. You begin with an element that appears in only one formula on each side of the arrow. In this reaction, sulfur and oxygen meet that requirement, while carbon appears in more than one compound. Starting with sulfur or oxygen simplifies the process and reduces mistakes. Before adjusting coefficients, it is important to list each element and count how many atoms appear on both sides of the equation. On the reactant side, there is one carbon atom, one sulfur atom, and two oxygen atoms. On the product side, there are two carbon atoms, two sulfur atoms, and one oxygen atom. Because these numbers are not equal, the equation is clearly unbalanced. This step helps identify exactly which elements need to be balanced, and in what order. Once the atoms are counted, we adjust coefficients to make the number of atoms equal on both sides. Here, sulfur and oxygen are balanced first by placing a coefficient of 2 in front of sulfur dioxide. Then carbon is adjusted last, resulting in 5 carbon atoms on the left. At the end, all elements have equal counts, which means the equation is balanced. The key idea is to change numbers in front, not inside formulas. We will practice balancing 5 simple equations by finding the correct coefficients to conserve the atoms on each side. If you look at the answer key, you can see how the coefficients work. For example, in the first reaction, we need 2 copper atoms to react with 1 sulfur atom to produce copper sulfide. In the second reaction, we must place a coefficient of 2 in front of both magnesium and magnesium oxide to balance the oxygen. The fifth reaction with magnesium and sulfuric acid is already balanced, meaning all coefficients are 1. This practice is like solving simple math equations to build your confidence. There are millions of chemical reactions, but memorizing all of them is unrealistic. Instead, chemists classify reactions based on common patterns. By recognizing these patterns, it becomes easier to predict what products will form. The 4 basic types shown here are combination, decomposition, single replacement, and double replacement reactions. Each type follows a general formula that shows how substances rearrange. Understanding these patterns helps make chemistry more organized and predictable. A combination reaction, also called a synthesis reaction, occurs when 2 or more substances combine to form a single new compound. The general pattern is A and B react to form AB. These reactions often release energy and are common in both nature and industry. A simple example is sodium reacting with chlorine to form sodium chloride or table salt. Combination reactions show how new substances can form from simpler ones. In a decomposition reaction, a single compound breaks down into 2 or more simpler substances. The general pattern is A, B breaks apart into A and B. This type of reaction is the opposite of a synthesis reaction, where substances combine instead. Decomposition reactions usually require energy, such as heat, light, or electricity, to occur. A common example is water breaking down into hydrogen and oxygen gases. In a single replacement reaction, one element takes the place of another element in a compound. This type of reaction follows the general pattern A, B, and X react to form AX and B. It usually occurs in aqueous solution and depends on the relative reactivity of the elements involved. If the replacing element is more reactive, the reaction will occur. In the example, chlorine gas reacts with potassium bromide. Chlorine is more reactive than bromine, so it displaces bromine and forms potassium chloride and bromine gas. Reactions like this are common in corrosion and metal extraction processes. A double replacement reaction occurs when 2 ionic compounds in solution exchange ions with each other. This type of reaction is also known as a metathesis or double decomposition reaction. The general pattern is AX and BY react to form AY and BX, where the ions switch partners. These reactions typically happen in aqueous solutions and are often easy to identify because something visible occurs. A solid precipitate may form, a gas may be released, or water may be produced. In the example, silver nitrate reacts with sodium chloride to form solid silver chloride, which precipitates out of solution, and sodium nitrate, which remains dissolved. Reaction rate, also called rate of reaction, is simply a measure of how fast a chemical reaction happens. Some reactions occur very quickly, such as combustion or explosions, while others occur very slowly, like rusting. A high reaction rate means the reaction happens fast, while a low reaction rate means it happens slowly. These differences help explain why some chemical changes are dramatic, and others are barely noticeable. According to collision theory, chemical reactions happen when particles collide with enough energy to break old bonds and form new ones. However, not all collisions result in a reaction. For a collision to be effective, particles must collide with sufficient kinetic energy and the correct orientation. If these conditions are not met, the particles simply bounce off each other and no reaction occurs. Reaction rate depends on how often effective collisions happen. Activation energy is the minimum amount of energy particles need for a chemical reaction to begin. Even if particles collide, a reaction will not occur unless this energy barrier is overcome. The energy diagram shows that reactants must first reach a high energy point before forming products. Only collisions with enough energy and the correct orientation result in a successful reaction. This explains why some reactions need heat to start. Not all chemical reactions happen at the same speed. Some reactions occur almost instantly, while others take a very long time to complete. The rate of reaction can be changed by adjusting certain factors. These include the concentration of reactants, the size of the particles, the temperature, and the presence of a catalyst. Each of these factors affects how often particles collide and how much energy those collisions have. Concentration plays a major role in determining how fast a reaction occurs. Concentration means the amount of reactant particles present in a specific volume. Compare the diluted and concentrated solutions. Which one produces a faster reaction, and why? The concentrated solution reacts faster. It contains more reactant particles in the same volume. This increases collision frequency. More collisions mean more chances for effective collisions, so the reaction proceeds faster. In the diluted solution, particles are farther apart, so collisions occur less often, and the reaction is slower. Particle size affects reaction rate by changing the amount of surface area available for collisions. Study Figure A and Figure B. Both contain the same solid reactant. Which one reacts faster, and what causes the difference? Figure B reacts faster. In Figure A, only the particles on the surface of the solid are exposed for reaction. In Figure B, the solid is broken into smaller pieces, exposing more surface area. More exposed particles mean more collisions, which increases the reaction rate. Higher temperature increases kinetic energy and reaction rate. Between room temperature and higher temperature, which reaction occurs faster, and what causes this difference? The reaction at higher temperature happens faster. When temperature increases, particles move faster and have more kinetic energy. This leads to more frequent collisions, and more collisions with enough energy to overcome activation energy. As a result, the reaction rate increases. A catalyst speeds up a reaction by lowering activation energy. Looking at the energy diagram, which pathway produces products faster, and why? The reaction with a catalyst happens faster. The catalyst provides an alternative pathway with a lower activation energy. This means particles need less energy to react, so more collisions become effective. The key point is that catalysts do not change the products. They only make the reaction happen faster. Activation energy is the minimum energy needed for a reaction to start. Without an enzyme, reactants must overcome a high energy barrier. With an enzyme, that barrier is much lower. This means more particles can successfully react at normal temperatures. Enzymes do not change the reactants or products. They simply make reactions happen faster by providing an easier pathway. This diagram illustrates chemical digestion in the human digestive system. Digestion relies on enzymes to break large macromolecules into smaller molecules that the body can absorb. Carbohydrates are broken down by enzymes such as amylase and disaccharidases into simple sugars. Proteins are broken down by enzymes like pepsin and trypsin into amino acids. Fats are broken down by lipase into fatty acids and glycerol, while nucleic acids are broken down into nucleotides. Each enzyme is specific to its substrate and works best in a particular environment, such as the stomach or small intestine. This shows how enzymes control reaction rate in biological systems. In catabolic reactions, enzymes help break bonds in large molecules, releasing smaller products. In anabolic reactions, enzymes help form new bonds to build larger molecules. The substrate binds to the enzyme's active site, where the enzyme changes shape slightly to make the reaction easier. After the reaction, products are released, and the enzyme is ready to be used again. Let us summarize the key ideas from the lesson. First, chemical equations use symbols and formulas to show reactions. with reactants on the left and products on the right. Second, chemical reactions follow the law of conservation of mass, meaning atoms are neither created nor destroyed. Third, reactions can be classified into 4 types: combination, decomposition, single replacement, and double replacement. Finally, reaction rate depends on factors such as concentration, particle size, temperature, and the presence of a catalyst. These ideas work together to explain how reactions happen and how fast they occur. Let us answer our first essential question about how reactions occur and how we represent them. We represent reactions using word equations and chemical formulas, and we classify them into types like synthesis and decomposition. The rate of these reactions is controlled by concentration, particle size, temperature, and catalysts. These factors affect how quickly reactants transform into products. So the key point here is that we now have the tools to describe and control chemical changes. To finish this lesson, you will complete an exit ticket with 3 questions. First, write and balance a simple chemical equation. Second, identify the specific reaction type of your equation. Third, explain how increasing the concentration of reactants affects the reaction rate. This exit ticket is your opportunity to show what you have learned today. Think of it as a final checkpoint to prove you are ready to move on.